If Wheatstone Bridge feels confusing or formula heavy, don't worry. By the end of this video, you'll understand it logically and solve this problem with confidence. This is the fourth video in our current electricity series. Think of a Wheatstone Bridge as a weight balance in the electrical world. I am sure we do not need to explain how a balance works. On one side, we place an unknown weight. On the other side, we keep adding known weights. When the needle of the balance comes to the zero position, we immediately know one thing. The weight on the left is exactly equal to the weight on the right. A Wheatstone bridge works in exactly the same way. The only difference is that instead of comparing weights, we compare resistances. And to be more precise, we do not compare individual resistances. We compare the ratios of resistances. A Wheatstone bridge is an arrangement of four resistors connected in a diamond shape. A battery is connected across one diagonal to supply current, and across the other diagonal, we connect a galvanometer to detect current flow. Let us now understand the general case of a Wheatstone bridge. That is, when the bridge is not balanced. The battery supplies a current I to the network. At junction A, this current splits into two parts, I1 and I2. A part of the current I1 flows through the galvanometer as Ig, while the remaining current continues through the upper right arm. The galvanometer current Ig then combines with I2 in the lower arm and flows through it as I2 plus Ig. Finally, all these currents recombine at junction C and leave the circuit as the same current I. This is how an unbalanced Wheatstone bridge operates. Now, the real insight comes when the galvanometer current becomes zero. That condition is called a balanced Wheatstone bridge, and that is where this entire concept becomes simple, logical, and powerful. In the balanced case, let us again consider a current I supplied by the battery. At junction A, this current splits into I1 and I2, just like before. Now comes the most important idea of a balanced Wheatstone bridge. At junction B, the current does not split towards the galvanometer limb. That means no current flows through the galvanometer. In other words, the galvanometer current Ig is zero. Since no current flows through the galvanometer, the current I1 continues entirely through the upper right arm. Let us call this current I4. Similarly, at junction D, no current is added from the galvanometer limb because the galvanometer current is zero, so the current flowing through the lower right arm remains unchanged. Let us call this current I3. Thus, the current entering the network splits at junction A, flows through the two arms without any current through the galvanometer, and finally recombines at junction C. This condition, where zero current flows through the galvanometer, is called the balanced state of the Wheatstone bridge. Let us now perform the KVL and KCL analysis of the balanced Wheatstone bridge to arrive at the relation between the resistances. We will start with the KVL analysis. Let us apply Kirchhoff's voltage law in the loop ABDA. First, note the assumed sign convention. Any voltage drop caused by current flowing in the direction of the arrow will be taken as positive. Now follow the blue marker along the loop. In the limb AB, the voltage drop is R1 multiplied by I1. Next, in the galvanometer limb BD, there is no current because the bridge is balanced. So there is no voltage drop across this limb. Now in the limb DA, the current I2 flows opposite to the arrow direction. Therefore, the voltage drop across R2 is minus R2 multiplied by I2. Once the loop is completed, we equate the algebraic sum of voltages to zero as per Kirchhoff's voltage law. Solving this equation gives R1 by R2 equals I2 by I1. Let us call this equation 1. Next, let us apply KVL to the loop BCDB. Again, note the sign convention indicated by the arrows and follow the blue marker. In the limb BC, the voltage drop is R4 multiplied by I4. In the limb CD, the current I3 flows opposite to the arrow direction. So the voltage drop across R3 is minus R3 multiplied by I3. In the galvanometer limb DB, there is again no current, and hence no voltage drop. Applying Kirchhoff's voltage law and solving, we get R4 by R3 equals I3 by I4. Let us call this equation 2. Now let us apply Kirchhoff's current law at junction B. According to KCL, the algebraic sum of currents entering and leaving a junction is zero. At junction B, I1 is entering the node and is taken as positive, while I4 and IG are leaving and are taken as negative. So we can write I1 minus I4 minus IG equals 0. Rearranging, we get I1 equals I4 plus IG, but for a balanced Wheatstone bridge, the galvanometer current IG is 0. Therefore, we get I1 equals I4. Let us call this equation 3. Next, apply Kirchhoff's current law at junction D. Using the same sign convention, we write I2 minus I3 plus IG equals 0. Since the galvanometer current IG is 0, this simplifies to I2 equals I3. Let us call this equation 4. Now we have 4 important equations. Using equations 1, 2, 3, and 4, we can eliminate the current terms. Finally, we arrive at the condition for a balanced Wheatstone bridge. R1 by R2 equals R4 by R3. Let us now understand the textbook derivation we discussed so far in a more logical and intuitive way using Ohm's law. We know one very important fact. When resistors are connected in series, the same current flows through all of them. So, by Ohm's law, the voltage drop across a resistor is directly proportional to its resistance. Let us first form the upper branch. Resistors R1 and R4 are connected in series. Therefore, the same current flows through both of them. So the ratio of voltage drops across them is delta V1 divided by delta V4 equals R1 divided by R4. Let us call this equation 1. Now let's form the lower branch. Resistors R2 and R3 are also connected in series and the same current flows through them. So by Ohm's law, we can write equation 2. Now let's connect these two series combinations in parallel across the same supply voltage V, so the total voltage across the upper branch can be written as equation 3. Similarly, for the lower branch, total voltage can be written as equation 4. Now let us rearrange this circuit to resemble a Wheatstone bridge and connect a galvanometer between junctions A and B. For the galvanometer current to be 0, the potential at junction A must be equal to the potential at junction B. That means VA equals VB, but the potential at point A is V minus delta V1, and the potential at point B is V minus delta V2. If VA equals VB, then it directly follows that delta V1 equals delta V2. Let us call this equation 5. Now, using equations 3, 4, and 5, we can conclude that delta V4 equals delta V3. Let us call this equation 6. Now substitute equations 5 and 6 into equation 2. We then get delta V1 divided by delta V4 equals R2 divided by R3. But from equation 1, we already know that delta V1 divided by delta V4 equals R1 divided by R4. Comparing these two expressions, we get R1 divided by R4 equals R2 divided by R3. Rearranging this equation, we finally arrive at the Wheatstone bridge balance condition. R1 by R2 equals R4 by R3. Let us now understand the use case of the Wheatstone bridge. This principle is commonly used to find the value of an unknown resistance. In this arrangement, the known resistances R1 and R2 are placed on the left side of the galvanometer. The unknown resistance R4, whose value is to be determined, is placed in the upper right arm of the bridge. A variable resistance R3 is placed in the lower right arm. Now the circuit is energized using a battery. We slowly vary the value of the variable resistance R3 until the galvanometer shows 0 deflection. When the galvanometer current IG becomes 0, the Wheatstone bridge is said to be in the balance condition. At this point, we note the value of R3. From the balance condition of the Wheatstone bridge, we know that R1 by R2 equals R4 by R3. Rearranging this equation, we can solve for the unknown resistance R4. So we get R4 equals R1 divided by R2 multiplied by R3. Thus, using a Wheatstone bridge, we can accurately determine an unknown resistance by comparing it with known resistances. Finally, let us solve the problem shown at the beginning of this video. By now, we have applied these ideas multiple times, so this problem should feel much easier. In the given Wheatstone bridge, all resistance values are shown, and the galvanometer has a resistance of 15 ohms. Our goal is to find the galvanometer current Ig. Let us start by applying Kirchhoff's voltage law to loop ABDA. First, fix the sign convention. Any voltage drop in the direction of the arrow will be taken as positive. Now follow the blue marker along the loop. In limb AB, current I1 flows through the 100 ohm resistor, so the voltage drop is 100 I1. Next, current Ig flows through the galvanometer, giving a voltage drop of 15 Ig. Then, in limb DA, current I2 flows through the 60 ohm resistor. Since the direction of I2 is opposite to the assumed arrow direction, the voltage drop here is minus 60 I2. The loop is now complete, equating the algebraic sum of voltages to 0, and simplifying, we obtain equation 1. Next, apply KVL to loop BCDB. Again, use the arrow to fix the sign convention and follow the blue marker. In limb B minus C, the current is I1 minus Ig, flowing through a 10 ohm resistor. So the voltage drop is 10 times I1 minus Ig. In limb C-D, the current is I2 plus Ig, flowing through a 5 ohm resistor. Since the direction is opposite to the arrow, the voltage drop is minus 5 times I2 plus Ig. Across the galvanometer limb DB, the voltage drop is minus 15 Ig. Equating the total voltage around the loop to 0 and simplifying, we obtain equation 2. Finally, apply KVL to the outer loop ADCEA. Once again, fix the sign convention using the arrow and trace the blue marker. In limb AD, current I2 flows through the 60 ohm resistor, giving a voltage drop of 60 I2. In limb DC, the current I2 plus Ig flows through the 5 ohm resistor, giving a voltage drop of 5 times I2 plus Ig. Now across the battery, there is a voltage rise of 10 volts. Since we are treating voltage drops as positive, this voltage rise is taken with a negative sign. Equating the loop equation to 0 and simplifying, we obtain equation 3. Solving the equations. Now we have 3 equations and 3 unknowns. Solving these equations simultaneously, as shown on the screen, we obtain the galvanometer current as Ig equals 0.004872 amperes, or Ig equals 4.872 milliamperes. I strongly recommend that you pause the video and carefully go through the solving steps shown here. Thank you very much for watching this video till the end. If you found the video helpful, please like, share, and comment. It really supports the channel. Do subscribe to the channel for more videos on basics of physics. In the next video, we'll understand how resistance varies with temperature. And if there's any specific topic you'd like me to cover, let me know in the comments.